Hello, welcome to the class of the, what was that? Industrial plant class, right? So we are doing some analysis on the industrial plant. One of them is laboratory. So we are working on laboratory nowadays. So let me start the Jupyter notebook, Jupyter lab. What happened? Okay. So let's go to the I don't think you can see my types. Okay. So let's go to Mount C drive. C drive has I plant, industrial plant. Okay. So we are having many files here. Jupyter, Jupyter lab. Hello, root. It's one of our students say that asked me that if I can share the IPython notebook file. So I will share you guys the file. So let me after I'm finishing this class, I will make a web page and I will share you the files using the shared drive. Okay. So let me go to the Python notebook. Why is the meaning? Okay. I think my computer is somewhat very slow. This is also so small. I will enlarge. Okay. So what we have done. Oh my. Sorry. Okay. Okay. So let me run everything first of all until this circle is not filled. It takes for a while, but I would say the problem is my computer is now so slow to continue this class. I don't know why. Okay, everything is all loaded. So what we have done last time is that we retrieved the laboratory promoter block table, right? So we could, so let me open this table. So we have the query ID. So this is the gene ID of the laboratory, and it has these sequences, right? So it has these sequences. So if you want to list up what kind of sequences in laboratory, then you can open this file, right? So we can go to this folder. Let me go to the folder C drive, iPlant, and what's it? Block table, right? Block table. Then you can see this situation of our blocks. So you may notice that, for example, these genes shares some blocks, so which means these genes are controlled by one element or one complex, or we can say one trans element, right? So these genes are interesting. These genes are interesting. So maybe we can take a look at what type of genes are so, what type of genes are sharing these elements. How can we do it? How can we do it? This must be not so easy, but let me try. Okay. And last week, we tried to visualize the upstream sequence of the promoter in this way. So we plot the promoter, positions, the promoter positions in this plot. So this x-axis represent the base pair, and y-axis represent the orders, right? So this is the orders of the promoter. So let me calculate the shared promoters. So maybe I have to. So we have to compare pairwise manner. So for example, I have to compare this one and this one, and this one and that one, right? This one and that one. So we have to use iter-tools, import combination, right? Combination and combination of laboratory promoter block table query ID and 2. Okay, combinations query ID, right? So if you just run this variable, then you will see this is iter-tools dot combinations. So this is a class. Maybe this represents the class. This is a class that having a combination. So maybe that is generator. Then you can just see what kind of combination is listed in this oh no, my computer is so slow, so I shouldn't run this command. Okay, sorry for problem. So I opened new IPython notebook because it is too slow to carry on the analysis. So I opened new IPython notebook, and I will load this laboratory promoter block table. So this was our last result. So I will just load this file rather than rerunning everything. So import the pandas and data frame that is laboratory promoter block table, right? So read CSV and laboratory. Okay. Then you can see this table again. So what I have done was that from iter-tool import combinations and combination query ID will be combination of laboratory query ID and two guys will be combined. Okay, so I say that this must be class or generator. So if I run in this way, then it will stop again. So I will just see 0 to 5. Okay. what I don't think my computer is good condition. I think something is weird. Okay, now I understand. Now I understand. I will stop everything. I will stop everything. I will restart. I will restart this corner, and I will show you what happened. Okay, run. Okay, so this looks generator comp query ID. So this is saying that iter combination something blah blah blah, and this is generator. The generator means that actually it do not run the command. It has planned to run certain command, so it do not consume any memory. But if I put here this command, then it will run every combination. So if I calculate the length of the query ID, then this must be the number of the all query. And if you want to calculate the all combination, then this must be in this way, right? Is it right? So this number should be comes out from the all combination. This is the problem, and this number is too much, and my computer memory is not sufficient to run this combination. So I need to think for a while. But I think I need to show you all the combination first. So I will limit the query of top 5. Okay, and run this again. Okay, then you can see these combinations. Okay, all combinations is coming out from these all 5. Okay, so this is how you do the combination, and this is the result of the combination. Okay, so then I can use for x and y in the iteration print x and y, right? No? What happened? What happened again? Run. Okay. So this is really generator. So generator, if you run again, then nothing happened, right? So because everything is done. So this is the plan. The plan is done, then plan is gone. Okay. So do happen, right? So plan is already gone. So to run again, then nothing is there. Okay. So this is what generator is. So I will merge these two. Okay. And this is so small. I will put here 10. So you will have this query and this query at the same time. So this is combination, right? And I will index this table. Index. index. Everything in life. Maybe you don't believe it. I didn't prepare anything for this lecture. Everything is all live, so there will be so much errors with regard to my code. So you can you can retrieve the blocks, right? So this is all blocks from your what is that? From your table, right? Table. And this table gives you back kind of list, but it is not list. So I will put 0 here. I will show you this again. Oh shit. Right? So it gives you in this way. So one iteration gives you back this one, and the other iteration gives you back this one. And I will check if x of these blocks and y of this block share anything or not. Okay. So live code is very hard. I know it. Split. Right. Then q x and x blocks, I would say x blocks and y blocks. So what I'm thinking is that if I grab any good information or any good knowledge from this analysis, then I will prepare manuscript also. Okay. The problem is it has blank because I intentionally add blank for good visualization, but this is problematic when you do analysis. So I will erase this blank. How do you do? How do you do? How do you erase this blank? For x in x blocks, x strip. Okay, good. And y blocks, x strip for x in y blocks. So that will be great if you can publish, if I can publish the paper out of this lecture, right? Good. Then how do you calculate certain overlapping of x and y? So I want to check if there is overlapping or not, right? So then you can set these x blocks and set y blocks. The set is kind of mathematical expression. So this set can be used in this way with and. This command gives you back what is common between x blocks and y blocks. Okay, and I will print this one. Right? So some have nothing. Some queries, some combination have nothing. but some combination have things, right? So I will imagine so common, okay, common. So print ranks and common. So I'm imagining that there is so much numbers all in this combination, right? So if you have more than zero like this, then it will have certain common element. This will be one that we are actually interested in, because these two combination sharing the promoter block, and it can be controlled by shared complex. Okay, then I will put if this length is larger than 0, then I will print x and y and comma. Okay. So this is so cool, right? This is so cool. This one sharing this one and this one, and sharing this with this one. So you can build network. This one and this one. So 21, 421, and 226, and 226 have 348. Right? Okay. Interesting. And I want to add more information. So this is kind of messy, having this all information. I will put here length, common length, and length of x and length of y, not x block, y blocks. Then you can determine what kind of so how much they are sharing. So in this case, everything is shared, right? Everything is shared. In this case, not everything is shared. Maybe you can put some kind of percentage, right? Percentage of query. So how do I calculate? Rank, common, and divide by length x log. Okay, and common by y blocks, right? Okay, very good. Maybe I can print here the headers. Maybe I can print here headers. So query ID x query ID underbar y, and common length. It is not length, common count, right? Common count and x block count, y blocks count, and ratio common to X block. radio, to Y block. Okay. Then you can print everything with open common no share the promoter to pairs text as file f file called f. Good. But I like to have CSV, so I put here separation. Separation with comma. Separation with comma. Separation is comma. Right? So if you run this code, then you will have where is that? Share. Okay, shared promoter pair. In this manner you will have. So let me check if I can run everything from tqdm import tqdm, and this is whole iteration etqdm query id, but this is what I limited for my analysis. I will erase. So this is the plan, right? So com query ID. This is plan. So if I run everything at once, then it will take a lot of memory. But if I just iterate, so do and dump, do dump, right? So my plan is already gone. Then I can, I say, use my memory more efficiently. So let me check if I can do this analysis in my laptop. Go. Right, you can see this all iteration. I don't know when it will over, but this iteration will be ended eventually, because I can see my memory is not that consumed by this one, right? So, oh my, this one. So Python just use 83 megabyte. If I run not using generator, then it will consume more than, I say, several gigabyte. So I will wait for a while and you will see the result. Okay, I stopped the iteration because it takes a lot of time, so that I moved the analysis to my server to run it. So I think it will be finished anyway. But in the middle of the analysis, I have the shared promoter pairs, even though I stopped in the middle. So I will I will retrieve, I will load data frame of shared promoter pairs like this. Then I can still observe the analysis result in the middle, right? So it is not finished yet, but we still can see the landscape of the analysis because I run this analysis 1 hour, and I think it takes a few days to finish because the number of the combination is like this number, but the iteration of this analysis is like 5,000 iteration per second. So it takes a lot of time. In my laptop, it was not 5,000, it was 10,000 iteration per second because it is slower than the server, right? But anyway, let's take a look at the in the middle of the result in the middle of the analysis. Then you can see the pairs. So one of our students is familiar with protein-protein interaction network. Is actually it is seriously be like, and because protein 1 and protein B is interacting based on the is2 hybrid, but this is A and B is related somewhat by region, that is the promoter block. In this case, you can see common count is 1. So only one count is shared and the other count is not shared. So the ratio is not that high. This ratio is not that high. And you can check the shape. Is 9,000 pairs is retrieved. But if we filter using these values, then we will have much less number of promoter, interactions. It is not interaction. It is, how to say, from gene pairs, right? So I will put arbitrarily, arbitrarily. How do you spell it? So choose any threshold. Right. So mask is N, M1, and M2. Then share the promoter pair and mask. Then you will see many protein pairs, gene pairs, 100 gene pairs are shared. So maybe one will ask me, do we have to choose any threshold? So this is up to my mind, or can we select this number more systematically? Yes, there is a way we can see the distribution of this number because this number is already we observed. Then maybe we can import matplotlib pyplot, plt, right? And plt hist. We show you the distribution, right? So you can see the distribution. Beans 100. I want to see 100 beans. Show. Then you can see, okay, majority of our data is residing here. So this is like kind of scale-free distribution, right? But this is the majority. But we want to see something more significant. So maybe you can put here this number as threshold. Maybe you can calculate the area under this bar or under this curve, and you can select certain number summing up these area is like 0.05. That is significant, right? So this is how you can select something. So, but in this case, I will just select 0.5. Okay, here. Then we will select everything this region. So this region will be, of course, very significant from the majority, right? Okay. So, oh, no, I don't need to delete it, right? I don't need to delete it. Undo. Okay. So I will rename this as significant. Sig. And maybe we can retrieve annotation. I think we already analyzed the annotation. Is it right? No. I was thinking that we already made dictionary that has annotation. No? This was blast. Yeah, okay. So I parsed the promoter information in this way. Okay. Then we need to retrieve the gene annotation from this. No. Maybe we have information in GFF. Let me see. Why it doesn't work? Hold on. Okay. So we can see this information. So your gene will have certain annotation around here. Product. Okay, so product. This also has the product column, so we need to parse the product because I checked here. They don't have any annotation table. So feature table. Let me check this feature table. Okay. Get feature table. No. Oh, it looks annotation, right? It looks annotation. But the problem is that, okay, our ID is shaped like this, and we can search. Oh, okay. Then we can use this information as annotation. Okay. Then let me remove this one. Data frame annotation. Annot. Feature table and contrast 간집. Separation is tab. Good. Okay, you have features. So this means that this will have the product accession. XM means mRNA, I think. XP means something protein. Okay, so I will remove every none in this product accession. Okay, is none. It's not. Right? It's not. Mask. I will. If you learn only this one, then you will select everything without any product accession, right? Because it's not. So it's not. If it's not is true, then this is not, right? So I will inverse this one using this symbol. Then you have all product accession. Okay, so I'll update or not. And this should be merged. Good. Or not head. Right? Then I will index it. Index. Not set index. Product accession. Good. Head. Then you can search this information using this information. Okay. Let's go back to data frame shared pair significant. Okay, then you have this ID and you have this ID. So I will annotate this X and Y. Okay. Then not X equal query X apply lambda X split. So I don't want to use this RNA something, and I will split it and I will select second one. Second one means 1, right? First one is 0. And I will use this information to retrieve annotation. ROC. Right? So, and which part is the annotation? Okay. Name. Weird, but name is annotation. Name. Wait. Okay. It completed in 1 second, and you can see annotation X will be like this. So we can imagine that if this much shared protein will be duplicate form of this one. So maybe this annotation will be same as this. Maybe I would say. Okay. Or something unexpected result can be happen. So I change this one and this. And done. And check. Right. So everything is all similar as expected. And let's export. Let's export to CSV and shared promoter pair with annotation. Not. Let's remove everything here, and I will check. Going to the folder I plant annotation. So if you check using this large form of Excel sheet, then it will give you more insight. So, as expected, this shared compound is kind of transcriptional variant, and maybe we can find another example. Let's see. Okay, these two is not that similar. So dual specificity protein kinase JAK2, I don't know what that is, but proline rich receptor like protein kinase PERK3 is sharing their promoter sequences. Then we can say, okay, these two protein is not that similar in with regard to the annotation, but the promoter composition is very similar. Interesting. And is there any other cases? No, only one is captured. But still interesting. These two is very interesting. So we can analyze further. And also, if you imagine more, I say more candidate, then you can lower the threshold. Is that right? So if you lower the threshold, then you will find more candidate. And this file is not finished, So this is our result is immature. So if I run everything, so this information is done from our server, then I will revisit the result to see what happened. So I want to automatically, I don't want to see by my eye to determine these two is similar or what. Then how do you do? apply lambda x. So this is very easy. So very quick manner. How do you do? So you can use set again and x or not x split. So you can split using nothing. Then it cut every space, right? And set x not y split. Okay. Then it will show you and maybe you can divide length of this one. Okay, and put x is 1. Okay, okie dokie. So it's shared index, so no need to worry on notation similarity, right? Good. Okay. So everything is like more than 80%. You can also put hist annotation similarity dot hist. So everything is like this, but maybe I can put here the threshold 0.6 and mask. Let's see. Okay, then we can see more easily. So I don't use my own eye to determine these two is different. So I can use this threshold to find these two, right? Maybe this one is also very similar each other, I would say. Okay, and I want to check if these two x m, right, this one, so this, okay, so this is in a scaffold. Scaffold, and this also in a certain scaffold. Okay. Unplaced scaffold. Unplaced scaffold means that they don't know which chromosome is contained this scaffold. Okay, so this one should be the scaffold accession, and this scaffold and this scaffold is different each other. And the start and end point is also different. So these two sequence is not transcriptional variant. These two is distinct genes that is sharing the promoter sequence. Very interesting. Very interesting. So we have this data frame, and I want to stop these two. Right? Comma. Okay. So actually, I don't say. So this is not that prepared lecture. So I'm very impressed with this result. So this is something we can expect, right? So these genes are all same. Genes are same, but the transcript is different. The transcription variant. Of course, your transcription variant should share the promoter sequence. Sometimes it is not because it doesn't start. Sometimes it doesn't start same start point. So if this number one start at thousand position, but the other this another transcription variant start in 999, right? Then this 999 start position doesn't contain certain promoter sequence, right? So maybe that promoter sequence is overlapping the start point. So this one has, but this one doesn't have. So it shows different number of the blocks. But this is very is very expected. So I was expecting this situation a lot. So I was thinking that only this kind of situation is happening, but luckily, how to say, very lucky. We find these two guys. These two guys, because I didn't learn everything, right? So I didn't learn everything, but we could select these two. So then these two distinct evolution, right? So this evolve. So this one evolved in this scaffold, maybe different chromosome. And this one evolved in this scaffold, different location, genome location. And this starting point is different, but they are conserved. Conserving. They conserve these sequences. This is very interesting. So I want print out. I want to print out the sequences more to visualize everything. Hit sequence query dot values. Okay. And for each in values print each. Okay, cool. Split. Okay. Hold on. Okay, so I will strip the E and print. Then we can clearly see the sequences. And maybe join. Okay. Strip each. No. Enumerate. Enumerate n comma. No. String instance. Ah. Okay. Then plus x string data. Okay. So we can observe each sequences very easily. So through this maybe we don't need to do this in this way. Are we? Okay. So we can just bias. Just bias. And first one. And first one. comma strip okay, and I will change this into set and set. Okay, then these sequences are all shared. All shared. So we don't know which one has exact function. However, maybe we can find certain database of these promoter sequences. Hold on. Okay, this is the. So actually, I was trying to find whether this sequence block is right to say this is really promoter block or not. But it was really hard to check if this is right or not. So we can see by our eye, maybe this is Tata box or maybe this is another things. Actually, I have no idea what is the typical form of promoters, but these blocks are really well conserved for some reason. So I was thinking that I can find some clue out of Google search, but it was very hard. Actually, I don't think they have very good database of the promoters because it is very hard to generalize whether these sequences right or not. So there is some engine to predict promoter blocks, but they don't have any sequence database. So I'm thinking I will build my own sequence database using this algorithm. I think this is a very good approach to retrieve certain well-conserved blocks in plant promoter region. So maybe I can build a database at the end of this class, I think. Anyway, let's wrap up this analysis, visualizing the promoter structure of these two sequences, right? These two genes. Okay. Leave it this way, and I will again I will call this result to retrieve exact promoter exact promoter position in upstream of gene. So I will load promoter info CSV parse CSV. Then now we have columns. This is much better, right? Okay. Then we can make index query copy. Good. Then I can load this one using, so they require RNA. Okay. Then I can, so this is query. So the query location, matched query location is here. So I will reset, no, I will call Q start, or copy it. Q start and Q end, right? Okay. And values for x and y in here, and PLT in plot, and I want to have enumerate. So enumerate gives you value for each iteration. So y value will be n x comma y comma n. What happened? What is happening? what is happening. And I don't know. X by u and y by u. In this case, I need to check whether I know this grammar in right way. Okay, 1, 2, 2, 2. So what I want to do is same y by u as n. But the problem is I want to print x comma y and n. I think I need to check the documentation of matplotlib plot. So x1 and y1. So this is x1 and this is y1. x1 to y2. Which means I have to put only x here and n comma n. Oh, okay. So this is the way we do the plot. This part only go x, this part only go y. So maybe I will change the label x1 and x2. And I will change this into y, right? Then it is more comprehensive. Okay, good. And this looks a bit messy. So I will sort by query start in place to. Okay, then it more ordered, right? So this is the plot x label. So this is the situation. This is the situation of the promoter existence and the upstream of certain gene, right? So we retrieved upstream sequence. Actually, I forgot the length of upstream sequence. It must be 500, right? So this must be minus 500. This must be 0. So this part is the start point of the gene, I think. Anyway, so upstream base BP, and I have to maybe change x6 into range 0 to 500, comma, list range 0 to 500. Do I have numpy here? I don't think so. Go to numpy, SMP, and numpy array. So numpy array, it gives you show. X6 range. Okay, so if you type in X6 like this, then this resulting. So I will show you everything. Copy. So this is original ticks. This is original ticks, but I will change this ticks into 0 to minus 500 because this is inverse. This is the inverse manner of our data. So I changed. Okay, so this is done. So this is the starting point hours, and this is the end point of hours. So this is the price of our promoter result, and this is the y-axis. Y label is promoters. Okay. Then we can make a definition: get plot promoters. And origin. And this origin goes to here. So, and tap. Test plus should go RNA minus like this. This one goes to like this, and RNA, right? Good. Okay, so the distribution of these two, actually it shares the sequences. I say one has 22 block and the other has 16 block, but the common count is 15. So if you compare with X block count, then almost more than 90% is shared. But if you compare with this one, then it is just 15. So it's like a 68%. But if you visualize this, then the existence of the promoter is bit let's say the location also is shared. The situation is completely different, but location of each block is well conserved each other. So we can determine, I mean, we can predict maybe the role of certain trans element is shared between these two genes. So I think that once the analysis using our server is done, now we already 2 hours gone. So then we will retrieve many genes that shared the promoter sequence like this. Okay, so I will finish my talk lecture until now. Next week we will check the other sequences, and we will visualize again, and we list up everything into one table. Okay, then I think we can build our own database. Thank you.